Knowing what we already know, you could easily figure out the velocity or the average speed of any of the vehicles that are driving past me right now. However, we do have a small problem. Many objects are going to change their speed as they travel. Some of them may slow down, like we see behind me right here at a red light. Others of them might be speeding up as they come through the intersection. So today, we need to be able to talk about acceleration.
Well, aloha everyone. Today we want to talk about acceleration. Now, what is acceleration, you might ask? What is the deal with this fancy word? Well, it turns out acceleration has a very specific definition in physics. Yeah, when we talk about it in normal life, we usually mean speeding up. But it turns out in physics, the definition of acceleration is a little bit more broad than just that. In fact, acceleration in physics is any change in an object's velocity. Any change in an object's velocity is going to be called an acceleration. So it turns out, yes, the way we standardly use it is one possible way an object's velocity could change. An object could speed up. However, an object can also just as easily slow down. And that would be considered acceleration as well. There's even another way that an object's velocity can change. You might remember that velocity is a vector, which means it has a direction. So it turns out, without speeding up or slowing down, if an object changes direction, that's also a form of acceleration. Speed up, slow down, or change direction.
You know, there's something interesting about the human body. You can't actually feel velocity. You can only feel acceleration. What does that mean? Well, when you're driving in a car, you can't tell when you're just going at a certain speed. Okay, sure, you feel the vibrations, you feel the bumps in the road, but you don't actually feel all that weird. The only times you notice that you're actually moving are when you're accelerating. That is, when you speed up, when you slow down, or when you make a turn.
So how do we calculate acceleration? What do we do in order to mathematically understand what acceleration is? Well, there's a formula for that, and it's going to be this, A. And acceleration is going to have a direction to it as well, so it's going to be a vector. I'm going to use A for acceleration is going to be equal to, well, it's any change in the velocity of an object. So if you remember, this triangle, this delta, means change in. You might remember that from math class. Divided by a change in time. If you know some calculus, that's going to turn into a derivative if you let delta t approach 0. But for now, we're going to stick to the algebra. So what does this mean? Any change in velocity. Well, how much is a change? How do you calculate what a change is? Well, you start off with your original speed, and you end up with a final speed. And if you want to know how much it changed, you just subtract the two. It's going to be the final velocity minus the initial velocity divided by the time, change in time. So, final velocity minus initial velocity divided by change in time. So your initial velocity is however fast you're going at the beginning and in what direction. Your final velocity is going to be however fast you're going at the end of the time interval we're looking at. And of course, delta t is going to be change in time. Or maybe you can just think of it as how long did it take to happen. Now, sometimes you're going to see this formula written this way, but it's exactly the same thing. Instead of a v final, sometimes they will just use a v. Minus, and instead of a v initial, sometimes they'll just use v naught. Divide by change in time, or sometimes they'll just put a t down there. Really, it's the same formula, it's just a couple different ways of writing it. It's the same variables moving around. It turns out that I prefer the vi and the vf, but people like College Board like to use v and v naught. Either way, it's perfectly the same thing. So let's see how this works when we have an actual situation. Let's imagine we have a car here. Boom. There's our car. And let's say the car is sitting here at a red light. So right now the light's red. But in a few seconds the light is going to turn green and the car is going to take off. So that means this car's initial velocity, vi, or maybe you can call it v naught, either way, it's perfectly fine, same thing, is equal to 0 meters per second. Because we said he starts off sitting at a red light. He's not moving. So 0 meters per second is his initial speed or initial velocity. In fact, we'll put a vector sign over that just to show he's not going anywhere, and direction, he's not going anywhere. It doesn't matter that much. Okay, so this car is going to start to move this way. And eventually when he gets somewhere over here, maybe it'll take him 10 seconds. After 10 seconds, maybe he's going to be moving at 15 meters per second. That's going to be his final velocity. Oh, and if this is velocity, it needs a direction. So to the right. Okay. I want to know, what is the car's acceleration? And I can solve that by using the formula above. So I have my diagram drawn out. The next thing I need is my formula. And the formula for acceleration is this. A with a vector sign over it is equal to v, or delta v over delta t. And that should have a vector sign. Now, sometimes if they tell me what the change is without telling me what initial and final are, I can just plug in right there. But it turns out I need a little bit more information here because this has v final and v initial in it. So this is equal to v final minus v initial divided by the time. In this case, it is equal to, I don't need to manipulate this equation at all, so I'm just going to go straight to plugging in numbers. V final is 15 meters per second. So 15 meters per second. Minus v initial is 0 meters per second divided by our time, our change in time is 10 seconds. That's how long he took to speed up. So this is equal to, work on the top first, 15 minus 0 is 15 meters per second divided by 10 seconds. And this is equal to 15 divided by 10 is 1.5 meters per second divided by seconds. Those seconds are going to combine and we're going to get something weird. We're going to get something like this, meters per second per second. In fact, we usually read it that way, but most of the time when we write it like this, 1.5 meters per second squared. But usually when we read this as meters per second per second. Now, I'm not stuttering there. The reason we call it meters per second is because this is a change in velocity. We're saying the velocity is changing by 1.5 meters per second every second. The velocity is changing by 1.5 meters per second per second. Now we also need to be a little bit more careful with direction as well. Acceleration is a vector, which means that it has a direction. You'll see here that our final velocity was to the right. So in this case, our acceleration is also to the right. We can see that because even though we didn't indicate it, we called everything to the right positive. So this 15 meters per second was in the positive direction. Our answer was also positive, which means our acceleration is also to the right. You can sort of think of the direction of acceleration as which way would you have to push this in order to make the change that's happening. Let's try another one and see where it doesn't come out so easily. Let's say this same car is over here now, and it happens to be traveling happily at 15 meters per second this way. So the initial velocity is 15 meters per second to the right, and I'm going to call the right positive again. And that's my positive direction. Okay, and then over here, there is another stoplight. And it happens to be red. So this car is going to slow down and it's going to come to a stop. It's going to go over here somewhere. And it's going to take a time of, let's make it, 7 seconds to come to a stop. I want to know what is the acceleration of the car in this situation. Well, in order to solve that, and apparently I lost my drawing. Here we go. Okay, so in order to solve this situation, to figure out what is the acceleration, again, I'm going to use the acceleration formula. A is equal to delta V over delta T, which is equal to V final minus V initial divided by time. Okay, again, I don't need to manipulate this one. I just need to plug in some numbers. So, V final, well, it doesn't tell you explicitly, but I know something. I know he's coming to a stop, which means I know V final is going to be 0 meters per second. So 0 meters per second minus V initial is going to be 15 meters per second divided by, what's our time? 7 seconds. This is going to be equal to negative 1.14, let's round that to 3 meters per second per second. So our acceleration is negative 1.143 meters per second. Why is this acceleration negative? Well, this negative indicates that the acceleration is to the left. So if the car is already moving and you need to get it to stop, which way would you have to push this car in order for it to stop? It would be back to the left. So that's why our acceleration is to the left. Now, sometimes if they give you acceleration, you might have to manipulate this equation to either find the initial speed or the final speed, the initial velocity or the final velocity. So because of that, I'm not going to go through a whole problem with you, but I will help you out with manipulating this. So you know A is equal to V final minus V initial divided by time. Usually we're going to start from here. That middle term really isn't that important unless they tell you specifically the velocity changed by this much, and you can directly plug in to change in velocity. Most of the time we're going to end up using this formula though. So let's say I want to solve for, let's go for V final. If I want to solve this for V final, first I need to move the t out of there. So I'm going to multiply both sides by t. Let's get a bit different color for this, times t, times t. And then this is going to go away, and we're going to rewrite. So t times a equals vf minus vi. Vector signs over these three guys. Okay, now that I have that, I can add a v initial to it, and I will get something like this. T times a plus v initial is equal to v final. I kind of skipped an intermediate step there just to show you plus vi. That goes away, plus vi ends up going down there. Okay, so we have v final is equal to t times a plus v initial. That's how you solve for v initial. If you wanted v final, that's how you solve for v final. If you wanted v initial, you would move it around so that you would get v initial by itself. You'll see there's a negative on there, so there would be one more step, and that would be to move that negative. Divide everything by -1 or multiply everything by -1. Now, this actually ends up becoming an important physics formula in the future. So, pay attention to this and keep this one in mind for future references. So that's the basics for acceleration. Mahalo for watching, and see you next time.